Okay, so g, the lowercase g, is the acceleration of gravity. We've called force of gravity mg. It's the same g. We calculate it as the universal gravitational constant times the mass divided by the radius squared. Well, if that's the acceleration of gravity, to go from acceleration to a force, we just add in another mass. G times m1 times m2 divided by radius squared. And that universal gravitational constant was down there at the bottom. Problem number 1 wants us to calculate the acceleration due to gravity. We know that is gm over r squared. G, it's our universal gravitational constant, 6.67 times 10 to the minus 11. We're going to multiply that by the mass of the Earth that they gave us, 5.98 times 10 to the 24th power, and then divide it by the radius of the Earth, 6.38 times 10 to the 6 squared. Be very careful how you put this into the calculator and make sure you're getting the same solutions I'm getting as well. When I solve this, I got G is equal to 9.799 meters per second squared because it's still an acceleration. The next question asks us to solve for the force of gravity. The force of gravity is g times m1 times m2 divided by radius squared. G, of course, is still 6.67 times 10 to the minus 11. It's on the formula chart, so you don't have to memorize it, but once you wrote it a few times, or you write it a few times, it'll come easier and easier to you. We're going to put for M1 as the larger mass. It's a good habit to be into. So when we get into circular motion, when we factor out the smaller mass, it'll be the one on the end. So the larger mass, 7.4 times 10 to the 22nd power, times the smaller mass, 55 kilograms, and then divide by the radius squared, 1.74 times 10 to the 6 squared. When I calculated this, I got a force of gravity of 89.665 newtons, because forces are still in newtons. You and your boyfriend, girlfriend each have a mass of 60 kilograms. You're sitting 20 centimeters apart. You want to calculate the gravitational attraction or the force of gravity, G m1 m2 over r squared. Now be careful, radius needs to be in meters. They gave it to us in centimeters, so you've got to convert it to 0.2 meters. 6.67 times 10 to the minus 11 times 60 divided by 0.2 squared. When I put this into my calculator, I got 6.003 times 10 to the power of -6. So not much gravitational attraction at all. This is the second type of problem now that we're going to see. First, we calculated for the formulas, and we can calculate for any unknown variable within that formula as long as there's only one unknown. But now we're going to look at ratiometric problems. So I'm going to take my formula gmm over r squared, and I'm going to turn everything into a 1. 1 times 1 times 1 over 1 squared. Then I'm going to plug in that change and see what the change to the force is. So if we double a mass, one of the ones become a 2, do the math, and you get 2 times the force. If we double both masses, 2 times 2, that will be 4 times the force. If we only change the displacement that's on the bottom, that would be 1 over 2 squared, or 1/4 the force. We've doubled the distance, we have 1/4 the force. If we half the distance, we get closer in, we would get 1 over 1/2 squared, or 1 over 1/4, which is 4 times the force. One object is doubled, and the distance then is cut in half, so we're going to put a 2 at the top, and a 1/2, don't forget it's 1/2 squared on the bottom. The 1/2 squared on the bottom becomes a 4 on the top times that 2, and we should get 8 times the force. The mass of one object is tripled, the mass of the second one is doubled, the distance between them is 1/3. So we're going to change one mass to 3, the other mass to 2. On the bottom, we'll put the 1/3, and don't forget it's squared. Now that 1/3 squared is 1/9, but the 9 comes to the top, we get 54 times the force. For number 2, the force is 20, and then they're going to tell us what the change to the force is. So that way our 1 times 1 times 1 over 1 square has to equal what the change is, right? So A is going to equal 1/2 because it went from 10 to 20. So our 1 times 1 times 1 over 1 square has to equal 1/2 to show that 1/2 change. I'm leaving a blank for where this is. So what is the change to that mass at the top to make it equal 1/2? Well, it's just simply 1/2 the mass. For the second one, I'm doubling the force. I'm going from 20 to 40, so my ratiometric change has to be equal to 2. If I'm only changing mass 1, well, if I double mass 1, I double the force, so it'll be 2 times mass 1. For C, I'm halving it again from 20 to 10. The radius is doubled, so I've got to deal with that doubling of the radius. So what does the mass at the top have to be that when it's over a 4, 2 squared, it's equal to 1/2? Well, 2 over 4 is equal to 1/2. So if I say the mass, well, I'm just going to rewrite it, I guess. I got 1/2, 1 times blank times 1 over 4, because I'm squaring that 2. What over 4 is equal to a half? 2. The mass is 2. It's doubled. For D, the mass didn't change. I'm sorry, the force didn't change. So my equation has to be equal to 1. If I double the radius, what does the mass have to do in order to maintain the same force? Well, if I'm dividing by 4 on the bottom, what do I have to put on the top to make it equal to 1? 4. 4 over 4 is 1. And then E, the force didn't change, it's still 20. Mass 1 changes and the radius is halved. So what do I put on the top if I've got a 1/2 square on the bottom? Well, 1/2 square on the bottom is the same as 1/4 on the bottom, and that brings a 4 to the top, so it'd be 1/4 the mass. 1/4 times 4 gets you the 1. What would be the effect on your weight on Earth if the Earth was doubled in mass but also doubled in radius? So my 1 times 1 times 1 over 1 square, I'm doubling the mass, so I've got 1, 2 at the top, and then double in radius, so I've got a 2 squared on the bottom. So if I've got a mass 1 becomes a 2 and the radius becomes a 2 but 2 squared, I would have 2 over 2 squared. 2 over 2 squared would be 2 over 4. 2 over 4 is 1/2. What would be the effect of the force between two objects if the distance between them was reduced to 2/3 of its initial value? So again, 1 times 1 times 1 over 2/3 squared. 2/3 squared would be 4 over 9, 1 over 4 over 9. And 1 over 4 over 9 is the same thing as 9 over 4. So 9/4. And if we put that in decimal form is always better than fraction. 2.25 times the force. For number 5, we want to go ahead and calculate all the acceleration and gravities for all the planets. So we're going to take our 6.67 times 10 to the minus 11, multiply by the mass they give us, and then divide by the radius they give us squared. So for Mercury, it'd be 6.67 times 10 to the minus 11 times 3.18 times 10 to the 23rd, and then divide by 2.43 times 10 to the 6 squared. So I'm going to go ahead and go down these and calculate them all really quickly, and then just check my calculations against yours. Again, these are the little g's for those planets. So like we use 10 for Earth, but how do the other planets or planetary bodies compare? And don't forget this is acceleration, so my units are meters per second square. Five A is going to ask us which planet would we weigh the most? Well, we know our weight is our mass times the acceleration of gravity. If our mass is held constant as we go from planet to planet, which one has the largest acceleration of gravity? I have it as Jupiter at 25.94. And on which planet would you weigh the least? That dwarf planet of Pluto, having the smallest acceleration of gravity at 0.42. Last page. What is the distance from the Earth's center to a point where you'd be 1/25th of what you are at the surface? If I'm only changing the displacement, if I've got 1/25th, so that's 1 over 5 squared, right? 1 times 1 times 1 over 5 squared. So my radius would be 5 times bigger. That would give me 1/25th. And if the radius is 6.38 times 10 to the 6th, I'm going to take 6.38 times 10 to the 6th, information from right underneath number 6. I'm going to multiply that by 5. And when I take 6.38 times 10 to the 6th power and multiply that by 5, I got 3.19 times 10 to the 7th. Now, if you got 319000000, change it into scientific notation where you have one number, decimal, two or three numbers, times 10 to some power. It's cleaner, it's better. Calculate the acceleration of gravity calculate the acceleration due to gravity on the surface of the moon. Acceleration of gravity is gm over r squared, so we're going to take g, our 6.67 times 10 to the minus 11, the universal constant, multiply it by the mass of the moon. I have that at 7.4 times 10 to the 22nd from the information above, and then divide by the moon's radius squared, 1.75 times 10 to the 6th. Don't forget to square the bottom. When I did that, I got 161 meters per second square. For number 7, what are the two equations that you now know that can be used to calculate weight? Well, before today, we would have said force of gravity is weight and force of gravity is mg. Today, we learned that force of gravity can also be calculated as g times m1 times m2 over r squared. I didn't worry about proving that they're correct. I just wanted to list them out. That was more important to me. What happens to the strength of gravity as you get farther from the surface of the planet? As you change your radius, remember radius is squared. If you get further away, it's reduced. It's not linear. It's the radius is squared in that formula. So what we should see is an exponential curve looking like the left side of a smile. And this works for if we're comparing displacement to the acceleration or displacement to the force, because they both have that same divided by radius squared.